Yeah.
Not sure what I'm going to do with my life once I aim this video. Yeah, so let me remind you, I'll send you an email about this. So on Monday, we will have a sort of end of the year celebration. If the weather permits, it will be out on the sort of green space, sort of south of Boyd. Open, and have some food, coffee, and maybe some other. All right, so today what we're going to do is the focus will be on the following theorem. So let me put up the theorem and then we're going to do some preliminary work. So let P be bigger than 2H minus T, okay? And again, lambda in XRT, so it's a restricted one. Then QR at lambda, this has a G structure. So we know it's a GRT module, but we don't know necessarily, we don't know if this module, this injective module for GRT will actually lift to G or not. And this is part of the Humphreys-Burma conjecture. So this is a special case of this famous conjecture by Humphreys and Burma, which says this should happen for all P, which was me in 1973, around that time. So this is actually part of, it's a more general case of the Donkin conjecture. So there's, remember, Donkin's tilting conjecture. Okay, so we call this D tilt. And this was made in 1990 at MSR. I think I mentioned it about 3 times. I'm going to write it down. Okay, so it says the following. So let lambda be a restricted rate. Okay. So then if you take the tilting module lambda half, you can restrict it down to GR. This is why you equal to QR half. Okay. And where lambda hat is equal to 2 P minus 1 rho plus W0. So Donkin made this conjecture in 1990. So this gives you a sort of a module, a G module, which actually restricts down to this projective incomposable module. And then Bendel, so logic. This was last year. We actually disproved this conjecture. So we found a counter count. The counterexample, as I mentioned once before, is for G2 and P equals 2. And actually, this is current work. We have more counterexamples. Hopefully, eventually come out soon. So stay tuned. Most likely, this seems to fail a lot in the cases where you have non-simply laced root systems. For simply laced root systems, maybe this holds in type A for all P. We don't know yet. Okay, so the more likely statement is that this will actually be more true in the simply laced cases rather than the non-simply laced cases for some reason. Okay, so our counterexample does not disprove this. So this statement could still be true even though the Donkin tilting module conjecture is not true. Okay, any questions on this? All right, so what I have to do is I have to give you some preliminary information, and then we'll go through a sketch of the proof of this statement over here. All right, so let's do some preliminary work. So let's see, trying to organize. Linear, the notes aren't linear. So. All right, so first of all, let's look at G module structures. So we're looking at G structures on injective modules. All right, so let V and W be G modules. Okay. So then, if I take COM GR of VW, this turns out to be a G module because this is sort of like V star tensor W with GR invariance, and so this becomes a module for G over R, because this is the G module, this is the G module, and where GR acts trivially, and then you just pull the action back to G. Okay, so it's a module for which GR acts trivially. Okay. All right, so moreover, there exists a G module. Namely, this module here, such that GR is M twisted electrons. Actually, the module M is this thing untwisted. Okay, and then you have to twist it back to itself. Okay, so you can actually write a module here, express this as a G module where M is just a G module and twisted R times. So I already said that. Okay, good. All right, now what you can do is you can sort of look at blocks, and you can define PR nu of M. So this is the sum of all submodules. Okay. With comp factors in on the same block as element. Okay, so we've actually seen this before. So M, I can write as a set of all nu in CZ bar, PR nu of M. So remember what CZ bar looks like. I'll just draw it using an A2 picture. It's this bottom thing, and then, so CZ bar is here. It's a sleazy bar. Okay. So because the action of the affine vial group is transitive on CZ bar, we can represent any weight in terms of the weight down here once we sort of reflect down, and the blocks are given by linkage clauses. So that's why we can represent the news in terms of this closure of the bottom alcove down. All right, so this is okay by language. All right, so what does this mean? Now I'm going to just apply to this. So that means that HOM GR of V of M is equal to the sum of V and CZ bar of GR new of VW. Okay. Now, what does this mean? It means that HOM new GR VW is the same as PR new of now twisted R times. Okay, so I've kind of incorporated the twist in here already. So I'm looking at the news in CZ bar, and then I'm basically twisting them at the end. Okay, to get this. All right. So now let me write on one more thing. Have people written this down already? So the next thing we're going to do is observe for T bigger than H. 0 is always in the interior alcove CZ. Okay. And the reason why is when I take unit product of 0 plus rho, like alpha 0 check. Okay, so I'm just doing this little unit product calculation. So clearly this is bigger than or equal to 0. And I get rho alpha 0 check here. Now, what's the Coxeter number? The Coxeter number is equal to rho alpha 0 check plus 1. Right? And so this number, rho alpha 0 check, is H minus 1. And we know that P is bigger than H. And P. Okay, so that means that 0 has to be in the interior of the alcove. Okay, so this is okay. All right. Okay, so now let's look at this thing. So if I take HOM via W, I'm not going to take, right here I've taken GR homomorphisms. Now I'm going to take actual G homomorphisms. So this is the same as first taking GR homomorphisms and then applying G to it, G over GR. Okay. And so, well, the things which are invariant under G, these are all trivial modules. So they're all linked to the 0 weight down here. So this is inside of GR 0 weight of V. Okay. So this is a bunch of trivial modules. Okay, so the G invariants are contained inside of HOM GR 0 of VW. Okay, that's the upshot of this. Okay, any questions on this so far? All right, so now we can start in on a sketch of the proof. Okay, so let's see here. Okay, so I did that. So let's start here. The sketch will come in like a few parts, so I'm going to try to map these out fairly carefully. There are some details which I won't be able to get to. Okay, so let me give you the main ideas. So the first thing is we're going to start with the claim. The claim is that when they take QR hat lambda, this is, sorry, let me start over. So let lambda n be an XRT. And so I'm going to look at this module. I'm going to look at Steinberg R tensor irreducible L PR minus 1 rho plus W0 lambda. Okay, so I'm taking the Steinberg module, the Arth Steinberg module, which is L P minus 1 rho, and I'm tensoring it with this irreducible representation. And it turns out that this has restricted weight also. So in some sense, this is part of D-filled, the conjecture that I gave you before. This should have a filtration by H zeros. That's the conjecture for all P. This is self-dual. So if it has an H0 filtration, it has a vial filtration. So if D-filled holds, this is a tilting module. And so it makes sense to look at this module in and of itself. So M is a G module. That's clear, I think, because the Steinberg is a G module, and I'm tensoring by an irreducible G module. All right, now I can state the claim. I'll just write it down here. So the claim is that QR hat lambda is a direct summand of F as GRT module. Okay, so I restrict this down to a GRT module and get a GRT sum. All right, now the first thing we should think about is, remember, this Steinberg is projected. So it turns out that this module is actually a projective GRT module. So M is a projected GRT module. It's actually an injective. So to show that this is actually summand inside of here, all I need to know is that the socle, this, sits inside of here. Okay. So it suffices to show that LR hat lambda is in the socle. Okay. The reason why is M splits up in terms of indecomposable GRT modules. You can tell which ones occur by just looking at the socle. Okay. How do I know that's in the socle? I just look at the Hom space. So let's look at the Hom, GRT, LR hat lambda into here, right? So Steinberg R, tensor L, E minus 1 rho, plus W0 lambda. So I just need to measure this Hom set. Okay, now I can move this guy on the other side and take the dual, and the dual of the Steinberg is the Steinberg. So I get LR hat lambda, that's Steinberg, L P minus 1 rho. Okay. And then I can move this one over to the other side. So I get GRT Steinberg R of L, let's see, minus W0 lambda. So this is the dual. Tensor L P minus 1 rho plus W0 lambda. And the highest weight here is the sum of these two highest weights, and it's P minus 1 rho. Okay. So it turns out that because you have this highest weight, it's actually a maximal vector. This is actually not equal. R here, too. Drop the R's everywhere. Yeah. There I got it now. Okay, so that's the first thing you show. You show that this is actually a direct sum and owns a GRT. Okay, so now we're on to sort of step 2. So what I need to do is, this is a G module, and I need to look at some sort of submodule inside of here, which is going to capture this. So that's kind of the next step. Okay. So let Q lambda be the injective hull L lambda as a G model. Okay. All right, so we have the following picture. So I have this L lambda, which is the same as LR hat lambda over here. So we know that this is a direct sum out of this, right? And so you have a G map which goes into here. Okay, so this, you actually have a map like this. Now, you also have a map which goes to the injective hull, right? It sits at the bottom. And so now you can use injectivity to extend this map. So there's a map phi which goes from M to Q lambda. Now, phi is injective. I'm sorry. Let's see. Oh, okay. So now what I want to do, maybe I'll move this over a little bit. Okay. All right. So let me move the phi over to this side here. It's a little bit better. And now I'm going to draw some things in. All right. Now, inside of here, we know there's a QR lambda hat, right? So inside of here is a QR hat. And so this sits inside the socle of this. Okay. And so now I can take phi and I can apply it to QR lambda and see what happens. Okay. So moreover, I take phi, which actually goes from QR lambda hat to Q lambda. This is the vector. Because This L lambda is the socket. So it has to be injected because we know that when I go from here to here and then go to here, it's an injective map. If there was a kernel, then this thing would have to go to 0. It's this common trick that we've been using on the long time. Okay, so we actually have a map from here to here, which is a GRT map. Okay. So let me erase this. So we have that, we have the following. So this, we know that this map on QR lambda is injective, so certainly an isomorphism onto its image. And we also know that phi of QR lambda hat is a GRT summand. Turns out okay. Since QR hat lambda is injective. GRT. Because, you know, if you have 0, phi, QR, hat lambda. Okay, so this is injective, so this has to split. Okay. All right. So let me give you the idea now. So here's the idea. This whole setup. So the idea is, first of all, that rho of M is a G mod, is a G module. Okay, so let's just check really quick. So M is a G module. This is a G module homomorphism, so certainly the image is a G module. Okay. And so the idea is we're going to show that the image on M is an indecomposable GR module. Okay. So if we take this G module, we show it's an indecomposable GR module. We know this is a summand as a GR module. So these two have to be isomorphic, or these two have to be equal. So then rho of them is rho by which will be okay. So this G module will realize Q hat R lambda. You know, this will lift to this module.
Is GR or GRT?
What's
Phi of M, we're going to show that it's an indecomposable GR module or GRT module.
well, it's not going to matter. So it won't matter whether it's GR or GRT. The indecomposable ability in both categories is the same. Okay, does this logic make sense? So I gave you a setup, and so I gave you a G module, which will actually realize this. Okay, so let's continue on. A little bit more to go. Okay, so let's continue on. Okay, so it suffices to prove that the socle over GR of phi of M is actually equal to LR of lambda. Okay, so I'm working in the GR category, so I can take off the half. Because if the socle is simple, you know, it can't split up into various indecomposable pieces, right? You know, if it had various indecomposable pieces, the socle would be, you know, have more irreducible representations. Okay, so if we show there's only one, it has to be indecomposable. Okay, so what do we have? So we have that the socle of phi of M. So this thing is going to, because this sits inside a QR Q lambda, Q lower lambda. So the socle has to be, the G socle has to be equal to L lambda itself. Okay. And what else do we know? We know that the GR socle of phi of M, the G socle has to sit inside the GR socle. Let's see, what else do we know? Let's see. Yeah, let's see, L mu is inside of the socle of GR phi M. Okay. So this module here lifts, this is a G module. This module actually lifts to G. We already saw that. So this implies that the L mu is contained inside the G socle. Okay. So the upshot of this is that we can only have one isotypic component inside of, I don't know if you remember the formula, but we have a direct sum over like L mu's, and then we have these twisted modules too. So from this argument, you can only have the isotypic component L lambda sit inside of it. Okay, so hence socle GR phi M is isotypic of type L. Okay, let me just write the formula out again. It's been a long time. So remember what this was. You take, there's a nice decomposition. So let's see, XRT. So let me do this in terms of signals. Right? Okay. So remember, you had this formula where you have this thing, and then you just palm GR L this thing into this module. Okay. So I don't know. Does everyone remember this formula? You just, what you do is you just look at how many times this thing appears in here, and then you just count them up. That's basically what you do. And this is a G decomposition, right? So if this thing is only equal to L lambda over here, right, then you only have one component, and that one component can only happen when sigma is equal to lambda. Okay, so that's what I mean by one isotypic component. Is that clear? All right, so we're using a bunch of things that we've seen in the past. Okay. All right, so far so good. Right. And so now I can actually write this out. So I wrote this out over here like this, right? And we can also break this up into blocks. So let me do it in 2 steps. So first of all, we have that there's only one isotopic component. This should be a lambda here. Okay, so we argued this point. And then now this one, I could break it up into blocks. And so this is the summation of mu and CZ bar of L lambda tensor GR mu L lambda. All right. Now, now what do we know? We know that phi of m is indecomposable for G because the sock of this is equal to L lambda. So note that phi of m is indecomposable. So essentially, because this is a block decomposition over here, you can check it out. You can only have one summand over here. So this implies there's this only one summand by using linkage. All right. So furthermore, and then we'll put all this together. So furthermore, we're analyzing the statement. Furthermore, well, what do we know? We know that K is isomorphic to the G homomorphisms from L lambda in here. Right, the socle of this, I'm just using this statement over here. Okay. So there's only one homomorphism from here into here. Okay. And we also know from what I said before that this is contained inside GR0 of 5. Okay, so we did that analysis and we showed that this is contained inside of there. Okay. So there's only one isotypic, there's only one component. So that component has to be the one where we have the 0 over here. And that's what it has to be. So hence, so from these 2 things. So hence, let me write it on the other side here. Okay. So conclusion. Big hands. Okay, so conclusion is that the GR socle of phi of m is equal to GR0. Let me write it this way to make it more consistent with this. So L lambda tensor hom GR0 of L lambda with phi. Okay, so all of this we get down here. Now, one thing to note is that the only thing we really used was P bigger than H up until this point. Okay, so let me just mark that down. So we only use basically P bigger than H, just up until this point. Okay, we don't use anything else other than that. All right, so let's keep going. So now, if I show that this is K, if I show that this homomorphism group is K, then we're done. All right? So if GR0 of L lambda phi of M is trivial logic. So then we have this GR cycle of phi of M is just going to be L lambda, which implies that phi of M is decomposable as, let's say, GR and GRT module. So that would imply phi of M. Okay, so that's how the logic goes. So it's this situation we have to prove. Okay. Now suppose this doesn't occur. Suppose it's called star. Does not occur. Okay, so there's another module. So there exists a weight nu, which is dominant in the same block as the zero weight. Okay. And nu is not equal to the zero weight, such that L nu twisted, which is L p to the r nu, is a compactor of H0 DR0 L lambda. Right. Okay, so if this is not K, it has to have some other composition factor, basically, and that's what I'm saying. Okay. All right, so what does this mean? So the implication is that this tensor, this, has to be a composition factor of M, right? So that means that L lambda tensor L u twisted R, which is of course L lambda plus QR nu, is a composition factor of Steinberg R tensor. Well, I'll just put the H0 in here. I'm using some bigger estimates. Okay. So this is actually a composition factor of phi of M. So it's a composition factor of M. M is Steinberg tensor L of this, but Steinberg tensor L of this is actually a factor inside of here. Okay. All right, and so the idea is you want to check the weights inside of this, and then for p bigger than 2h minus 2, this can't happen. So I'll leave that as for exercise. So the idea now is to actually check the weights. This module So you can check this by using like Bios character formula, or you use some weight estimates.
Thank you, Dr. Lawrence. Thank you, Dr. Lawrence.
Did you know this, the character of this thing by Bios character formula? Or there's some weight estimates. And then the upshot of this is for P bigger than 2H minus 2, lambda plus PR mu is a weight if mu is actually equal to 0. Okay, so this is where you use the P bigger than 2H minus 2 inside. Okay, so maybe we should sort of analyze the proof. So this basically gives you a sketch of the proof. All right, so I guess if you believe this, then for P bigger than H, we'd love to know the answer. We think that for P less than H, like Donkin's tilting module conjecture is going to fail. So we actually have some examples where we may be able to get up to P less than H. So this seems to be a more reasonable bound. So you can get down to here. Now, maybe this is too strong. That's one question to ask is, that's a pretty strong condition because, just because this module is indecomposable, that doesn't mean the socle has to be simple, right? So maybe this condition is too strong. I don't know. So the question is whether this condition needs to be removed and dealt with in a more effective way. I don't know. So this is sort of a question mark in terms of trying to lower the bound. Okay. I don't think you're going to be able to sort of change this at all. Yeah, I think this is about as good as you can do. So the obstruction sort of comes in sort of trying to show that this only has the trivial module. The socle could conceive it, the GR socle can, how do I say this? Well, let me say it this way. This one may or may not be true. But the point is that we really do want to, I don't know if you can actually improve these estimates or not. That's a question. I think a lot of people have tried. A lot of people have actually looked at this proof and tried to make it so that you can even lower it to 2H minus 3, for example, or 2H minus 4. So, okay, are there any questions on this? I find this a really fascinating topic. It's kind of, it's almost addictive. You think it's going to be true, and then you keep working on it, and then you may find a counterexample. Who knows? Okay. All right. So the next thing I want to do is I want to move towards a Steinberg tensor product theorem for injective modules. And now that doesn't really make sense because they don't need to be like, you can't necessarily lift the Gmod. So we try to do the next best thing. Okay, so let me at least state this. Maybe we can do some preliminary work on this. So this is called Steinberg tensor product theorem. Injective, say GRT modules. right. Okay, so let me state this as a proposition. So we're going to actually go through the proof of this proposition next time. It's kind of neat because we use spectral sequences to actually prove this. Okay. All right, so the idea is the following. So let lambda 0 be a restrictive weight. And just lambda 1 be just an arbitrary weight in x of t. Okay. So then there exists an isomorphism of GRT modules. And let me write that isomorphism out for you. Okay. So, so I'm going to start with r plus 1 lambda 0 plus, I guess, PR lambda 1. Okay. All right. Now, remember, if I take QR plus r plus 1, this is a GR plus 1 T module. Right? Okay. So let me just say it this way. I'm going to restrict this action down to GRT. Okay. So as a GRT module, we get a nice decomposition. So first of all, as you would expect, you take this down to QR lambda 0, and then you tensor not how QR hat lambda 1, and this is actually Q1. Okay. This one twisted R times. Okay, so let's analyze this for a second. Okay, so first of all, this is definitely a GRT module, no problem, right? What about this one? Well, so this one is a G1T module. Right? And so let's think. So now I want to, well, GR is going to have trivially on it. So that means it could be a GRT module. So with GR action trivial. So this corresponds to this, and because GR acts trivially, it becomes a GRT module. Yeah. So this becomes a GRT module. So it has a trivial GR action on it. So basically, you're just taking the weights. That's all you're doing. Okay, so you should compare this with, so let's compare with the situation where I have this over here. So lambda 0, XRT, lambda 1. I guess it should be, let's just say I take something in X plus. All right, so what happens here, I think if I take L lambda 0 plus PR lambda 1, now I use Steinberg's tensor product theorem, right? Twisted R times. Okay, so by Steinberg's tensor product theorem, you get this decomposition. Now this is stronger because this decomposition is as G modules. not just, GRT modules. So this is an actual isomorphism as G modules over there. Okay, so for irreducible modules, you actually, on the level of irreducible modules, you have a decomposition like this, but it's for G modules. Now, it turns out that if you can lift all this stuff, then actually this will be okay as G modules. Right? We don't know whether these modules lift or not. We just know for P bigger than 2H minus 2. Okay, any questions on this? All right, so next time we'll actually prove this point over here, and then we'll sort of move on. We'll be able to definitely complete the section on injective modules. We have a little bit of time we may talk about. Okay, so let's stop.